Okay, so before going into the details of video processing, I would like to take a broader look on the task of perception using neural networks. This has been a field of extremely heavy research and application activity going over the more or less last decade. And even though this is definitely a vibrant field and there are lots of advancements, I think that in this point in time we can draw a few lines on what is required to do these tasks of, I will focus on this talk on image processing, so on perception, on understanding what is going on in images. And even though we are still making progress and good progress in improving the performance versus accuracy trade-off, which is always an engineering trade-off, recent surveys in this field that have now gathered much more information than what was available 2 or 3 years ago are kind of setting the guidelines into what are the requirements for neural network processing of video. So for me, this was an interesting observation. You can see here two works. One on the left-hand side is regarding the number of parameters of the network, and the right-hand side about the operations. So I'll try to explain what we are seeing. On the left-hand side, the y-axis is accuracy of the task of image classification across the well-known ImageNet database. And the x-axis is the number of parameters. These lines, they represent, I would say, generational improvements of the underlying network architecture. Interesting to see that they all have a knee at around 20 million parameters. From the first, this is starting from the ResNet generations, going over to the improvements of ResNet, the NAS searches, and so on. And this is the recent work of EfficientNet by Google. All of them have the knee of performance versus a parameter count at around 20 million parameters. This is, of course, both indicative of the architecture as is indicative of the data set itself. But if we assume that ImageNet is a reasonably representative data set for image processing, then we get kind of a ballpark in terms of number of parameters. The other survey regards a number of operations. If we take out the outliers of these huge VGG networks that you see on the bottom right-hand side, and we look at the number of operations versus accuracy, which is the y-axis, we see once again that there's a trade-off, and it remains quite constant, that takes around 5 giga operations per frame to achieve, I would say, in advances over time, what we consider reasonable accuracy, but to get to that accuracy, we usually need around 5 giga operations. And since these are convolutional neural networks, and this is the dominant factor in image processing, we should normalize it by pixels. ImageNet is the data set is 224 by 224 pixels, or 50K pixel. So we divide the number of operations per pixel, we get to 0.1 mega operations per pixel. This is a rough number. It changes by the meta architecture, which we attach to the feature extractor, which is what these networks are usually used for. And of course, we can play with the accuracy. But taking this basic number and multiplying it by a reasonable input size, let's say 2 megapixel, and a reasonable throughput, which for a sensor is typically 24, 30 frames per second, we get a number of around 5 teraops per second of required net compute capacity to process video feed. So these are kind of interesting guidelines. So this is what we need to do in terms of processing. The other question is why? Why? I'll start first for why doing it on the edge. When this field started to emerge seriously around 2 or 3 years ago, most of the focus was in the cloud, and it's starting to shift to the edge. And why is that happening? So it's usually use case dependent, but it's related to bandwidth limitation and response time limitations in most cases. Bandwidth can translate to either you don't have bandwidth or it costs a lot. So I've chosen to analyze here a scenario of a smart city deployment. I've seen a couple of those. Let's say I want to deploy 1 million cameras around London. This is a realistic use case. And I want to see what's happening in the streets. Maybe there's pollution, maybe there's violence, maybe I just want to see where there's activity and optimize the traffic. So if I just naively transfer all the data that I'm deploying from the cameras over wireless, I need I need to transfer around 100, after compression, around 100 gigabytes per day. These are tremendous costs. Nobody does that, and especially not at scale. So what can you do? You can do some form of filtering at the edge. For instance, motion detect. This is the basic of the basics. The problem with these kind of naive processing schemes is they miss a lot and give false alarms. And you still remain with a lot of payload that is going to the cloud, where you still need to process that data and, of course, manage it. So we get to very high costs, and this is one of the factors that is limiting the scale of the deployment of these kind of projects today. If somehow we could magically process the same level that we have in the cloud, have it on the edge, within the reasonable constraints, which I'll explain later, but roughly speaking, a few watts and a few tens of dollars, which is a top that you can put on this kind of camera in both aspects. And this still only the interesting information. We can reduce 2 or even 3 orders of magnitude in terms of data throughput, reducing both the cost and the complexity on the cloud side. So we still need connectivity, but you don't need it as intense. And then going over cellular network makes a lot of sense. Now, naturally, you get other very interesting benefits. Real-time response. This, of course, is use case dependent. For instance, in industrial automation, this is a critical metric. In public safety, less so. In public safety, for instance, privacy and security are also important, and not having to transfer all the data to a central location where it's vulnerable is very beneficial. So each vertical has its own needs, but in many cases, we are starting to see trends of going to the edge to process. Now, I've started to talk about energy limitations, and I'll try to explain how to derive them. So I'm trying to look at it from 2 directions. One is how low can we go in terms of energy consumption, and this, of course, is driven by the required processing, which I've tried to outline in the previous slides, and the efficiency of the processor. And efficiency is that famous TOPS per watt figure, but not as you usually see it on a datasheet level. It's a processor that can theoretically do, let's say, 30 trillion operations, and is thermally limited to 30 watts, so the number is 1 teraop per watt. This is not the reality. You should measure the efficiency by seeing actually how much performance you're getting on a real task and divide it by the actual power consumption. So this is the lower bound of how low can we go. How low should we go is determined by what's good enough. No point of being excellent if you can just be good. And this is determined usually by what the platform can support. There are 2 main constraints to that. I'll refrain from talking about battery operated at this talk, but even at wall-powered operated, the first limitation is usually the heat. In this case, I'm giving sort of a set-top box. It can be a router, an NVR, or any other edge box which is used in analytics, video on the edge. These boxes are usually limited thermally by what is convenient for a person. There are a few standards around this I've taken here from ISO. Typically, 10% above body temperature, and this means for a reasonable human being, 40 degrees Celsius. And if you look at the data that I've tried to put here, taking a reasonable junction temperature on the eye, which is 85 degrees, and typical mechanical characteristics of around 6 to 10 degrees Celsius per watt of heat transfer. So we are getting to a few watts, something between 4 and 7 watts of allowable power dissipation. I'm assuming that this kind of a box, which usually concentrates a number of sensors, would want to process maybe 2 high-resolution videos or 8 VGA streams. These are typical numbers in this industry. We get a compute requirements of around 10 trillion operations per second. Dividing these numbers, we get that the desired efficiency is around 1, 2, 3 teraops per watt. Taking from a different angle, the power constraint, these systems that are at the edge are usually they don't have access to free AC power as much as they want. They have usually outlets which provide them, converters which provide power from the outlets. Typical wall adapter ratings are approximately 10 watts for something that doesn't break every second week. taking some headroom, we get around 8 watts of consumption, which this dome camera in this case can consume. You already have content there. You have usually some sort of the image sensor itself, motors, communication, some management. So what we're left with room for expansion, if it's usually around 5 watts, we get around 2 or 3 watts which are available. And now going back to the desire to process one video stream real time, we once again get similar numbers of 1 to 2 teraops per watt, which are required to achieve this, to accelerate this system. Okay, now I'll try to explain why do we need high resolution real-time processing. This is not always the case. For instance, if I'm trying to unlock my phone, this is also happening on the edge, and I'm centering the phone in front of my face. I don't need lots of pixels. I'm tolerable to a delay of 200, 300 milliseconds, it's fine. And I don't really need real hard real-time or high resolution. But there are many cases in which I do need this, and I'll try to show some of them. So the next few slides are going to be about automotive, and then I'm going to go over other directions. So first, I need high resolution to look far. I want to see small objects from distance. In this case, once again not working, I'm trying to, this is a driving assistance system, which I'm putting on a front-facing camera of a car. And I want to see the worst-case scenario, which is a toddler when I'm driving at around 80 kilometers per hour, which is with some safety margin. This is probably the requirement. These are not probably, these are actually typical requirements for this kind of systems. I want to do comfort braking. Otherwise, I might cause an accident with someone hitting me on the back. So I need around 60, 80 meters of braking distance. Now, how do I derive the required resolution? I start by taking the angle of view, which is typically 120 degrees for front-facing cameras. Distance, we've said 60, 80 meters, and then we can divide the picture into pixels. A typical neural network, assuming that it gets a few shots in detecting the object, we can, of course, doesn't have to be on the first shot, but within a few shots, 8 pixels are more or less enough. So we can calculate the distance in between pixels for a 0.6 meter toddler, which is a reasonable goal, and we get to a requirement of 4K wide image. One might argue, why are you working so hard? Check. Okay. Why work so hard when you can just look to the front and focus on the area which you're interested in? And of course, this is a viable strategy. However, there are other things on the road, not the things that we are focusing on, but things that might come from the side. And this is defined by standard, not emerging, but advancing standards like Euro NCAP, most notably, defining scenarios from, for instance, cyclists that are coming from your right or from your left, and you would want to identify them the same way that a human being would have. And of course, not at the same distance. That doesn't have to be 80 meters. I don't need to see a cyclist coming from 80 meters, but I want to see it, in this case, 60 degrees, someone coming from 30 meters, which give me a few seconds to respond. So this is what's limiting us in terms of angle of view. Now, after going over the trivial cases, having more details gives us ability to do more interesting things. A few examples from driving would be reading signs. There's a trend in the industry to heavily rely on mapping. This is, of course, has its advantages and disadvantages. I don't think it's a viable strategy on its own. You wouldn't want to lower the performance of the driving assistance system compared to a human being. So you want to be able to read signs, maybe license plates for public safety or for kind of insurance applications. And even thinking one level deeper, we as human beings, we tend to see lots of details. For instance, if someone is driving in the car in front of me, I can see if he's talking on his mobile phone. I don't do it, but some people do it. And when they do it, they are distracted, and they might present more risk. In order to be able to see those details, we need to have pixels inside the image. And to extract them using the same feature capacity that we have used on the low resolution image that has had lots of, or which was focused on the image in the database without extending feature capacity, we gotta have multiple scales of the image. Some is very broad perspective, understanding this is a tiger or leopard, not sure. And one that is actually able to, at a finer grain, which is able to decipher the direction of the gaze. Is it coming from me or not? I guess this is the application for this image. In more practical cases, taking here to the field of public safety, you want to see who people understand their faces. There's a huge difference between having 8 pixel of 8 by 8 pixel of a face than 32 by 32. When they do pose estimation, violence detection, things like this, and they all require seeing more details, not only focusing on one specific object, because you don't know where is going to be the interesting event. Now, I'll talk a little bit about what is the state of the art in this industry of embedded AI. So we've talked about efficiency. There's been a lot of talk in the industry recently about how to measure efficiency. The most common or straightforward way to measure your efficiency in TOPS through what is calculate on a given task. Could be image classification, object detection, semantic segmentation, all kind of tasks that we are doing on video. The top square frame is something that is theoretically given from the algorithm, and then measure on the device the frame per second and the actual power consumption. This is the only, I would say, fair way to do it. Still not a common practice in the industry. Disappointingly, in recent benchmark, this was not yet included. If anyone is following this field, for instance, MLPerf, we are trying to push hard in this direction. But if you do take numbers that are available, this is what you see on any available edge device that I'm aware of. Something lower than 0.1 teraops per watt, and in the best cases, 0.3 teraops per watt. And this is far from satisfactory for the use cases that I've described. Another limitation of the way we currently design processors is they're very DRAM bandwidth intense. They're trying to access both the intermediate results and weight maps, the parameters for the weights constantly, and this creates bottlenecks on the interface. So you could see, even today, you could see all kind of interesting approaches on how to solve this. What we're suggesting at Hailo, and this is what we're basing our architecture on, is something that we call a structure-defined data flow. And the idea is that instead of having a central processing element and an external memory and going back and forth from that memory, you're using the fact that the neural network is a distributed problem and distributing your calculations along the device, both in spatial and temporal domain. The basic concept of the architecture, which we've presented recently, is that we have a sea of resources, compute, memory, and control element, and given a structure, a specific context of a neural network, we are decomposing it into the layers. It could be naively, as same way defined in TensorFlow, some a bit more complicated, and building a data flow that goes from one element to the other in the device. And this really shortens the paths that you're traveling to access data. It distributes the computing, so you get to very high parallelism, and you can work at much more reasonable frequencies and much lower power dissipation, and still get to very high performance and very high efficiency. This is the first device that we have presented and already working at the hands of customers. We call it Hailo 8, not creative on the names, but it's it tries to bridge that gap that I've presented in the beginning of my talk. So it is an extremely capable edge device in a small form factor. It's 26 tera operations per second. So it's even after taking some utilization figures on the utilization of compute, you still get to numbers that which meet these requirements. It contains, or it can operate without an external memory. It can contain everything inside the device that is required. And this really, really lowers the power consumption. So we're getting to 3 teraops per watt measured system level on real tasks. I will give some examples. and while still maintaining high degree of flexibility and programmability of this solution. A side effect of being of keeping this fairly simple and low power design is that we are able to target very high quality in terms of the system. We are targeting this device also to fit in automotive context. This requires both safety and safety mechanisms and fitting into high temperature. We're targeting this to qualify to ASQ100 grade 2, which is an automotive standard, which basically says the device should sustain 105 degrees Celsius ambient temperature. Given that silicon stops working at 125, if you're consuming too much power, you have no chance of getting there. And this is what is required to get AI processing at this scale to fit into something like a front-facing camera, which is exposed to heat and doesn't have any active cooling mechanisms. Taking these numbers into more concrete settings, so these are numbers that we have presented in the Embedded Vision Summit in Santa Clara, comparing this to two pretty good solutions that are available, almost available in the market. In this case, we took the NVIDIA Javier, the Google Edge TPU. As I said, this industry is not yet very good at reporting on power and performance. They usually report on one of them, not together. But so there's not many available results, but these are available and open. I'll not put you the links, but if anyone is interested, I can share it. And what we are showing, I'll try to walk you through the graph, 3 tasks here. Image classification, this is a ResNet 50 neural network. Object detection on MobileNet SSD on HD, 720p. And semantic segmentation, an FCN 16 based network on 1080p. The numbers that you see on the bottom are the performance. So within that small form factor, and without any external components, we're able to reach a performance which is same as you get from top performing edge devices. And on the bars, you can see the efficiency, the actual measured efficiency, ranging between 10 to 20 or even 30x better power efficiency compared to comparable devices on the market. And all these tasks run at, I think, between half and 1.5 watt. So they're definitely feasible within an edge scenario. Okay, that was my talk. And now, if you have any questions, feel free. Okay, so this is already sampling for major customers. We expect to run production during the first half of next year, including the automotive qualification, which is a challenging and interesting task, but needs to be done. And yes, we have an SDK at beta stage that over I think a dozen customers are already working with. Not perfect, but functioning. The good question about precision, and this is I should have stated this specifically. All these numbers I've given are on 8-bit integer. All the accuracies, both for us and the others, are within less than 1 or 0.7% of accuracy of the regional network, so it's a fair comparison. We have flexibility. I think all of the devices also have flexibility in terms of how to represent, but from our research, we find that in almost all use cases, for most of the for almost use cases and for almost all layers in the network, proper working with 8-bit is good to recreate the original results for inference. Yes. Okay, so we've not disclosed the number of the SRAM size publicly, but we support a few tens of millions of parameters on the device. All the tasks that you've seen are running completely on device without external memory. And you're right that to be more accurate, you should count actually all the operations in ResNet, for instance, the element-based operations are, I think, less than 0.1% of the operations. So if you have a specific bottleneck there, then yes, should be accounted for, assuming that you're eventually comparing apples to apples on the network level. I think it's a fair comparison. I'm trying to keep it simple, but concretely this would add less than 0.1%, I think. I think more. Okay. Yeah, I'm not talking about depth-wise or things like this. I'm talking about just additions. Okay. Yes.
So you mentioned you do the data path. This takes advantage of bandwidth on account of latency, right?
Why is that?
Like, since you're aligning all the multipliers in a row, instead of all of them working on the same layer, then you take away some latency, you get a penalty in the latency, but you get better throughput, more images. But sometimes, I think especially for the ADAS industry, then you want to process only a single image before the next one arrives. So how can you
So there are multiple techniques how to address this. We filed a few patents on this, but one that is public in some use, for instance, I think designers are using this in these FPGAs. For instance, they do tile processing. They divide the image into small parts and then start to pipeline it. So there are multiple ways to overcome this. Some are more efficient, some are less efficient. But you're right that there's, if you're doing it naively, then you're getting basically as the depth of your pipeline. But there are many ways to reduce this into reasonable numbers. Yes?
Can you elaborate on the deployment of the neural networks? Like, what is the flow of the Hailo end?
Sure. So basically, our tool chain is meant for running inference. So we're starting from, let's say, TensorFlow trained model, translating first of all the structure of the graph, something like a cafe-like representation, which is hardware aware, and what was asked before, the question of numerical translation. This has, in many cases, some back and forth with the developer to optimize the performance. The peculiar part that we have is that spatial resource mapping that I've illustrated. This is something that you can think of it as a sort of place and route phase, which the toolchain is doing, and distributing the problem on the elements. But afterwards, you get a binary that runs, and then just you infer it on the device.
Yeah, to speak back on that question, I think one of the key challenges facing more the data center AI inference like GraphCore and Habana is the software ecosystem and the ability to overcome the NVIDIA ecosystem. To what extent that challenge exists in your environment? To what extent you basically able to overcome it?
So this challenge definitely exists. I don't think that to the extent that it is in the data center, since embedded is a world which is always about optimization. There are other fronts which are related to interfacing with data flows and system management, which are completely non-related to the neural aspects, but also need to be handled. For instance, I talked about safety. Yeah, all this core is ASIL-B will be certified, but it's ASIL-B designed, meaning that I am signing on the failure in time rate and how to identify error. This has theoretically nothing to do with neural networks. Actually, in practice, it does have, and it's really interesting topic, maybe another day. So besides just being fit for TF Lite, or which is the standard, we are a bit more diverse than that, but things like these frameworks, we need also to fit into other environments. This is in 60 or something % of the companies invested in what you just described. Yes?
Actually, NVIDIA, for more questions. Yes. NVIDIA is the JSON Nano, which costs $100. Suppose I can do anything I want with the JSON Nano. How does Hailo 8 compares against the JSON Nano price-wise?
Okay, so JSON Nano that you're describing is a system. It's a bit different.
No, it's a module. I can integrate it with.
Yeah, no, I'm doing it for the it's a full system. This is very competitive, I would say, and much less power. If you're good with the JSON Nano, and you're good with the cost and good with the power, then I don't have much to offer you.
So price-wise, you are comparable to the JSON Nano.
I've not said that. I said we're competitive.
Let's thank our speaker.